All right, welcome to the Explainer. Today, we're going to roll up our sleeves and build a multi-site enterprise network completely from scratch. We're following a classic CCNA practice lab, so we'll be configuring everything step by step, all the way from getting basic internet access to automating the routes between different offices.
Okay, so here's how we're going to tackle this. First, we'll get our bearings by looking at the network blueprint to understand the end goal. Then we'll get our sites connected to the internet. After that, we'll link them all up with some secure site-to-site tunnels and make the whole thing smart with dynamic routing. And of course, at the very end, we'll test everything to make sure it all works perfectly. Before we even think about typing a single command, we gotta know where we're headed, right? It's super important. So let's take a look at the big picture, the final network topology we're aiming for. So this right here, this is our blueprint. You can see we've got multiple sites, and each one has its own little world of routers, switches, servers, and so on. The goal is to get all of these separate islands talking to each other and to the outside world, both securely and efficiently. This is basically the giant puzzle we're about to put together, one piece at a time. Okay, first things first, our users need to get on the internet. Simple enough, right? Well, there's a catch. All of our internal devices are using private IP addresses, and those just aren't allowed on the public internet. So how do we solve that little problem? The magic solution here is something called Network Address Translation, or NAT. And to be more specific, we're going to use a flavor of it called Port Address Translation, or PAT. The best way to think about it is like a receptionist at a big company. You've got hundreds of employees inside, but when mail goes out, it all uses the one main company address. The receptionist, that's our router, keeps a little log of who sent what, so when a reply comes back, it knows exactly which desk to deliver it to. That's PAT in a nutshell. And setting this up is actually a really logical three-step process. It's super straightforward. First, we have to tell the router who is allowed to go to the internet. We do that with an access list. Second, we have to define our boundaries. We basically tell the router, hey, this side is our inside network and this side is the outside internet. And finally, step 3, we apply the master rule that just ties it all together. And this single line of code right here is where all the magic happens. The key part, the absolute secret sauce, is that little word at the end, overload. That is what tells the router to do PAT, to let all those hundreds of our internal devices share that one single public IP address. Without that overload keyword, we'd run out of addresses in a second. And boom, here's the proof in the pudding. A successful ping to a public address like 1.1.1.1 confirms we have a path to the outside world. But what's really cool is the Show IP NAT Translations command. It gives us a live look inside the router's brain, showing us exactly how it's mapping our private IPs to the public one. It's working! Okay, moving on to our next challenge. Our different office sites can get to the internet now. That's great, but they can't talk to each other. We need a way for them to communicate directly and securely, and to do it right over the public internet. And for this job, we'll use GRE tunnels. A GRE tunnel is basically a private virtual hallway that we build right through the public internet. It takes the data from one office, wraps it in a new package addressed to the other office's router, and sends it on its way. It's like a direct private connection, but it's all virtual. Now, to build these tunnels, you have to be precise. Each tunnel needs a clearly defined source and destination. These are the public-facing IP addresses of the routers at each site. This table right here lays out the exact blueprint we're going to use to connect our network. So what does the configuration look like? Well, we create a new virtual interface, which we're calling Tunnel 12. Then we define the tunnel's source and destination using those public IPs from our table. And here's the clever part. We assign a private IP address to the tunnel interface itself. This creates a new logical point-to-point link that our network can use later on. And here's our verification. A successful ping to the private IP address at the other end of the tunnel, and we get a reply. This confirms our virtual link is live, our private hallway is officially open, and data can now travel directly between Site 1 and Site 2. Okay, our sites are connected, but we've still got a pretty major challenge. Right now, our routers only know about their directly connected networks. We need a way to teach them about all the networks across our entire enterprise, and we need them to update this information automatically if something changes. The tool for this job is a dynamic routing protocol called OSPF. The easiest way to think of OSPF is like a super smart GPS for your network. All the routers running OSPF talk to each other,
They share maps of the networks they know, and then they all work together to calculate the most efficient path for data to travel. And again, it's a simple, logical process. First, we kick off the OSPF process on the router. Second, we give the router a unique name, an ID, so its neighbors can identify it. And third, we tell it which of its connected networks it should start advertising to those neighbors. So here in the configuration, we enable OSPF with router OSPF1, but the critical part is the network commands. These tell OSPF which interfaces to actually run on. By specifying the local LANs and our new GRE tunnel networks, we're telling the router to start forming neighbor relationships and advertising these specific routes. This is the moment we're waiting for. The Show IP OSPF Neighbor command shows a state of full. This is fantastic news. It means our routers have found each other, they've become neighbors, and now they're successfully sharing their network maps. They're officially cooperating. All right, let's move to our final verification. We've put all the pieces in place: internet access, site-to-site tunnels, and automated routing. Now it's time to see if we have one cohesive, intelligent end-to-end network. To do that, we have to look inside the brain of the router, its routing table. This table holds all the best paths to all the destinations it knows about, and it should now be filled with all that great information it learned from its OSPF neighbors. And the proof is right there in the routing table. We're looking for routes that start with a capital O. That O means the route was learned dynamically via OSPF. This router now automatically knows how to reach remote networks across the enterprise by sending traffic right through our GRE tunnels, all without any manual static routes. And this is the ultimate test. A ping from a PC in one location to a server in a completely different location, and we get a reply. It works. This confirms full end-to-end connectivity. The reply shows that NAT, our GRE tunnels, and OSPF are all working together seamlessly. Our network is officially fully operational. So let's just recap what we've accomplished. We started with a bunch of isolated office networks and, in a few logical stages, we built a fully connected enterprise. We provided internet access with NAT, linked our sites with GRE tunnels, and automated the routing with OSPF. We now have a cohesive and intelligent network. So we've successfully built the roads, and we've installed the GPS system for our network's data. That leaves one final question to think about. With all this traffic now flowing freely and efficiently, what's the next critical layer we need to consider to make this a truly enterprise-grade, production-ready network?